back at it again with some more calculus. Today we're actually going to do calculus. This lesson is called the 12-6 Fundamental Theorem of Calculus. There's on page 784. So the first concept that we need to really talk about before we actually get into the fundamental theorem of calculus is what's called an antiderivative. Antiderivative. So an antiderivative is just the opposite of a derivative, obviously. Opposite of derivative. It will often be represented as a capital F of x, where, remember when we had just a lowercase f of x, we had, was just a function. And when we did f prime of x, that was the derivative. F prime of x. So all an antiderivative is actually just the opposite direction. So, for example, let's say we have a function 3x squared. Now our derivative said that we would take our power and multiply it out front. So my derivative would be 6x and my exponent would go down 1. Okay. The antiderivative does the opposite. My power goes up 1 and I have to divide by my new power. So my antiderivative in this case would be x cubed, because I would increase my power from 2 to 3, and then I would have 3 divided by 3 out front. I have to divide by my new power. Instead of multiplying, I'm dividing. So my antiderivative is the opposite direction. With that being said, let's do an example. Let's say we have 8 over x to the negative 8 over x to the 9. Okay. Well, first, my thing's not written in the correct form. We have our x down there in the denominator, not doing a whole lot. So what if I just had rewrote this as negative 8 times x to the negative 9? Again, I need a negative there because it's actually in the denominator. Now, the antiderivative says that I would have to increase my power by 1. So negative 9 plus 1 would be negative 8. So my new exponent's going to be negative 8. And then I have to divide by my new thing. So I get negative 8 out front divided by negative 8. Well, negative 8 divided by negative 8 would just be 1. So my antiderivative would be x to the negative 8, or 1 over x to the 8. And we can easily check that, because if I find the derivative of the antiderivative, they would undo each other. So this would again be x to the negative 8. I need to multiply my negative 8 out front. Negative 8 times x, and lower my power by 1. Negative 8x to the 9th, which as we said earlier would be that way. So the derivative of the antiderivative would just be the function. And it doesn't matter which order you go in. Antiderivative and derivative just undo each other. That being said, we had a whole bunch of derivative rules, and the same thing applies to antiderivative rules. So antiderivative rules. Let's see. First one, well, the first one's pretty easy. It's the power rule for antiderivatives. Power says that if f of x is x to the n, antiderivative is going to be x to the power of n plus 1 divided by n plus 1. And then we get a plus c after. Now this plus c is going to come up a whole bunch, so you're just going to hold on with me, and we're going to do the rules first, and then I'll talk about the plus c, because it's in every rule. Okay. Next one. Constant multiple. So let's say I have my function is something like f of x equals k x to the n. My antiderivative would still be x to the n plus 1 over n plus 1, and my k would just be out there as well. But typically you would just end up doing k divided by n plus 1, but so just having a constant out in front doesn't affect anything, and then of course you have a plus c, plus capital C. Okay. Next one we get the, last one we get the sum and the difference. So let's say our f of x equals, let's see. Say if I have f of x plus g of x, and I know that the antiderivative of f of x is big F of x, and the antiderivative of g of x is big G of x, then if I just find them both individually, I would just get big F of x plus big G of x, as you guessed it, plus C. If I can do my antiderivatives of each individual one, just do that. You don't have to worry about it too badly on either one. Okay. Now, this plus C thing is interesting. This plus C part. The reason we have to include it is big C stands for unknown constant. We have to represent every single number that exists because, let's say I had 2x squared plus 4. And I were to find the derivative of that. I would get, let's see, my 4 would go away because it's a constant, derivative says that. My exponent would put out front, so the derivative of that, if this is my f of x, my derivative would be 4 of x. Now, if I were just given the derivative, and if I were just given the derivative of 4 of x, and I had to find the antiderivative, the only thing I'm going to know for certain is that this part has to be 2x squared. I don't know what that constant is, because, again, what if it wasn't 2x plus 4? What if it was 2x plus 5? The derivative is still going to be 4x. So I have to include this plus c because there could have been some constant out here before things got derivativized. So the plus c just covers all of our bases. It could be 0, it could be 10,463. You never know. So we have to include that plus c. It represents all those constants. So let's do an example. Example 2, antiderivative rules. So first we get a function. How about x squared plus 8x, x squared minus 8x plus 5. That's as good as any. Now again, the sum rule says what you think it should. I can just do the antiderivative of each individual component. So, antiderivative of x squared. Again, we need to increase the exponent by 1, so I get x to the 3, and then I'm going to divide by 3. So I get 1/3 x cubed. Here, my exponent is just 1, so I need to get x squared. I still have my 8, but I have to divide by my new exponent, so 2. So I get 8 divided by 2, so 4. So I get minus 4x squared. This one's easy. I just got to slap on a component, so 5x. And then, of course, I get a plus c. So I do my antiderivative. And big F of x. Now, over the next couple things, you're going to see why I kind of struggle with that 12-5 section. Because with the sums and the limits, I never did area under a curve that way. I never did integrals that way. I did them this way. An integral, if I have f of x dx from a to b, that's the exact same thing as the antiderivative of x plus c. Oh, if I don't have these. This would be what's called an indefinite integral. It's indefinite because I don't know where it ends. I don't have a definitive start and stop. I don't have those things. But all that is just the antiderivative plus c. So instead of writing out all of that work with like your 64 over 6 and all that fun stuff we did in the last notes, yep, you just need to find the antiderivative. I'm sorry. But let's do it as an example. Let's do an example. Example 3. Indefinite integral. So, let's say an egg is dropped from 30 feet. The 30-foot egg drop. And someone actually took the time to model the equation as velocity in regards to time equals negative 32t, where t is in seconds. Okay. Find the position of the dropped egg. Find position. Okay. So here, all we really need to really work on is finding that antiderivative, because we can find the area under that curve, because if that integral represents the area under a curve of my negative 32t, my integral would tell me that exact position in regards to time. So, negative 32t. Now, I'm going to write dt instead of dx because we're not differentiating in terms of x, we're differentiating in terms of t. Okay. So, my t value, remember my t is just going to go up in an exponent for antiderivative, so I get t squared. My negative 32 stays out in front, but I'm going to divide by my new exponent, which is 2. So I get negative 32 divided by 2, which would be negative 16 t squared, and then of course I have to add that c, that constant. In this case, say my constant was 30, I can now in theory figure out what specific time is going to hit the ground. So if my c in this case was a constant that I knew, which we were given this time, I get negative 16 t squared plus 30. And if I were trying to find when it hit the ground, well, what would the position be when it hits the ground? How high would it be in the air? Naturally, it would be at 0 for its height. And then I could just do minus 30 divided by negative 16 and then the square root of t. So let's see. Yes, I did right. Oh no, it's super easy. It's way easier. What the heck is it asking? Oh, yeah, never mind. Yeah, minus 30 divided by 16, so I get t squared equals 30 over 16, square root. 30 divided by 16, square root of that, 1.37 seconds. For the egg to hit the ground, which is actually not bad. that's the idea of an indefinite integral. As you get all those things, you get that constant value. Now, here's the thing. What if, instead of an indefinite integral, we could calculate the exact area? Well, we can with a, as you guessed it, a definite integral. So we can calculate the area under any curve with a definite integral. So let's say I have f of x dx from a to b. Area under that curve would be the antiderivative of a minus the antiderivative of b. And this is a definite integral. With these, you do not need to worry about c, because you would end up just subtracting it from both sets. Indefinite, include that c at the end. Definite, don't need the c. You would just get, again, like I said, c minus c. So, let's do it. Example 4. Oh, yeah, that definite integral thing I just wrote, that's what's called the fundamental theorem of calculus. That's where this chapter is named about. It's all about that idea. So example 4, area under a curve. So let's say we have y equals 4x cubed, and I need an interval, let's say from 1 to 3. So we did a whole bunch of stuff previously where we're doing all these different limits and sigma notations, all that stuff. Well, we don't really need any of that stuff because we can just go like this. From 1 to 3 of 4x cubed dx. Find the antiderivative. So my exponent goes up 1, so I get x to the 4th. And then I have to divide by a new one, so I divide by 4. So the antiderivative is just x to the 4th. Now, remember, I have to do antiderivative of a minus the antiderivative of b. So I get a to the, I think that makes that round actually. I think it's b minus a. It is b minus a. So I get 3 cubed minus 1 cubed. This one's easy because there's only one term, but if there were multiple x terms, you'd have to keep it all organized. So I get 3 to the power of 4, which is 84. 1 to the power of 4, which is 1. 1 minus 84, so my area would exactly be 83 units squared. So that's way easier than doing the limit and sigma notation. I apologize. I'm sure a lot of you are kind of probably annoyed that I taught you that, but I do what I can to make you upset. Okay. And then we're just going to do one more example here, and that'll be it for today. Quick one. Example 5, integrals. Let's say I have the integral from 2 to 3 of 9x minus x cubed dx. And here's a little bit more of a complex one, more challenging just because there's one extra step, there's 2 different x terms. So again, I need to do the antiderivative, and I need to do b minus the antiderivative of a. So first I need to find the antiderivative. So here my x would go up a term, so I get x squared. And then my 9 would be divided by my new exponent, so 9 divided by 2. Here my x would go up a term, so x to the 4th. And then I would get it all over 4. And I would have to do it from 2 to 3. So let's keep them separate. My f of b, I need to do 9 halves of 3 squared minus 3 to the power of 4 divided by 4. That's my b side. And I also need to do 9 halves 2 squared minus 2 to the power of 4 over 4. That's my a side, and then I need to subtract them at the end. So, 3 squared would be 9. 9 times 9 would be 81. 81 divided by 2, which would be 40.5. 3 to the power of 4, which as we said is 81. 81 divided by 4, which is 20.25. 40.5 to minus 20.25, so I get 20.25 there. 2 squared, which would be 4. 4 times 9 is 36. 36 divided by 9 would be 18. 2 to the power of 4, I believe it's 16. 16 divided by 4 would be 4. So 18 minus 4 is 16. So then I get 20.25 minus 16, so 4.25. I'm just going to double check my answer there in the book before I close out. This is example 5. Shoot. Oh. You guys are already yelling at me because I'm dumb. 18 minus 4, that's 14. This should be 6.25. Okay. And that would be a definite integral. If I just had the indefinite, that would have just been that 9 over 2 x squared minus x to the 4 over 4 plus c. If I didn't have my endpoints, I couldn't have done anything more with it. Otherwise, yeah, that's honestly calculus. It's just a whole bunch of different algebra. All a calculus really is just adding that last step and just incorporating those derivatives into an integral. Okay. So, I recommend this way, but if you really, really enjoy doing that algebra and memorizing those integrations with those i's and those I squareds and those limits, go for it. The same process. You get the same answer both ways. Okay, that's all I got for you. Have a great day.